Now, in our previous video, we talked on Fourier series for periodic function of period 2π. Now we'll be considering Fourier series for non-periodic function of range 2π. Now we are given this question of f of x is equals to minus pi from the range of minus pi less than x less than 0 and x from the range of 0 to pi. And to solve this, we recall from our formula that we've had before now that we have two formats, one from 0 to pi, from 0 to 2 pi, and the second from minus pi to pi. Now let's rewrite the question. It says f of x is equal to minus pi from the range of minus pi less than x less than 0 and x from the range of 0 less than x less than pi. Now we can see this is a form of discontinuous function. Okay, so it starts from minus pi to 0 and from 0 it ends at minus pi. So we can say in the effect that these two combined together we give minus pi less than x less than pi, and we can see that this is the same as this. So this will be the formula we are going to be using to evaluate a naught, to evaluate an, and to evaluate bn. In our last two videos we used the formula for 0 less than x less than 2 pi because the question we have was from 0 to 2 pi. Now let's solve. Minus pi less than x less than 0 and 0 less than x less than pi. So this is a form of discontinuous function. So let's solve for a naught, and our a naught is 1 over pi integral of minus pi to pi f of x dx, 1 over pi integral of minus pi to pi f of x dx. Now from the question we can see that we do not have anything that spans directly from minus pi to pi, but we have from minus pi to 0 and from 0 to pi. So we can split it further and say this will give us 1 over pi integral of minus pi to 0 f of x dx plus 1 over pi from 0 to pi of f of x dx. Now 1 over pi integral of minus pi to 0, the f of x from the range of minus pi to 0, from minus pi to 0 is minus pi. Okay, minus pi dx plus 1 over pi integral of 0 to pi f of x dx, and the f of x ranging from 0 to pi is x dx. So we can now solve these, and we have 1 over pi integral of minus pi to 0 multiplied by minus pi dx plus 1 over pi integral of 0 to pi of x dx. Now pi can cancel out pi, so we'll be left with 1 into minus pi of 0 of minus 1 dx plus 1 over pi integral of 0 to pi of x dx. So when we integrate our minus 1, okay, when we integrate minus 1, we have minus x. So we have 1 into minus x from the range of minus pi to 0 plus 1 over pi. When we integrate our x, we have x squared over 2 from the range of 0 to pi. So we have upper limit minus lower limit, upper limit minus lower limit, and our upper limit is 0 minus our lower limit is minus pi. So in essence, we move on and also imply our upper limit, which will be pi squared over 2, and the lower limit will be 0 squared over 2. Now this will give us 0 minus pi plus 1 over pi into pi squared over 2, because this will turn to 0. So we have minus pi plus pi over 2, and this is a naught. Now we have been able to evaluate a naught. Okay, minus pi plus pi over 2 can also be simplified further, and minus pi plus pi over 2 will be minus pi over 2. Now we have been able to simplify a naught. It's now time for us to simplify an. Now an from the formula is 1 over pi integral of f of x cos nx dx from minus pi to pi. So we have 1 over pi integral of minus pi to pi of f of x cos nx dx, and we recall that our question is f of x is equals to minus pi x, this one reading from minus pi to 0, and this reading from 0 to pi. So since it is a discontinuous function, we can split it further to give minus pi to 0 plus 0 to pi. So with that done, we can now substitute our corresponding f of x. Substituting our corresponding f of x, we have that an is equals to 1 over pi integral of minus pi to 0, and f of x here will be minus x plus nx dx plus 1 over pi integral of 0 to pi, and f of x here is x plus nx dx. So let's focus on these now, and we solve for an. This pi can cancel this pi, and be left with minus 1 outside, integral of minus pi to 0 of cos nx dx plus 1 over pi integral of 0 to pi of x cos nx dx. Now we can see that this is straightforward. However, this will be splitted into two as u and v, and we apply the integration format of uv to give u v1 minus u prime v2 plus u prime prime v3, and it continues. So we know that our u is equal to x and our v is equal to cos nx. So our u prime, that is differentiating x, will give us 1, and our u prime prime, that is differentiating 1, is 0. And our v1, which is integrating cos nx with dx, will give us sin nx over n, and our v2, which is integrating v1 with dx, will be integral of sin nx over n with dx, and apparently this will give us minus cos nx over n squared. So we will take this first to solve. So we have that an is equal to minus 1, and integrating cos nx is sin nx over n, as we have done here, and we are dealing from a range limit of minus pi to 0, plus it is now time to solve this using the formula. So we have 1 over pi outside, and then we start with our u, which is x, multiplied by v1, which is sin nx over n, minus u prime, which is 1, and v2, which is minus cos nx over n squared, from limits of 0 to pi, 0 to pi. So simplifying further, we have that an is equal to minus 1 into sin nx over n, 0 to minus pi, plus 1 over pi, x sin nx over n plus cos nx over n squared, from 0 to pi. Now it's time to introduce our upper limit and subtract it from our lower limit. Now we can see that we have two functions to introduce upper limit and lower limit in. So starting with the first, we have minus 1, introducing upper limit of 0 into sin nx over n. We have sin n into 0 over n minus sin n into minus pi over n, plus 1 over pi. Now we introduce the upper limit of pi into this function. So wherever I see x, we put pi as pi sin n pi over n plus cos n pi over n squared. And we introduce the lower limits, minus 0 multiplied by sin n0 over n plus cos n of 0 over n squared. So the next thing is to reduce the terms. So we recall that sine n 2 pi is equals to 0 and cos n 2 pi also is equals to 1, and sine n of 0 is equal to 0, as well as cos n of 0 is equals to 1. What goes to sine to pi, sine n of pi is equal to 0, and cos n of pi is either plus 1 or minus 1. Okay, it is plus 1 when n is even, and it is minus 1 when n is odd. So in that case, let's nullify as many as we can to reduce the equation. So sine n of 0 occurs here, and we can say sine n of 0 is 0. So this cancels out to give 0. Sine n of minus pi. Okay, sine n of minus pi is the same thing as minus n minus sine n pi, which we will treat that a even and odd function in our next video. So this is equivalent to 0. Sine n of pi, sine n pi is occurring here, and sine n pi is 0. So this is also 0. We have cos n pi here, which has the possibility of plus 1 or minus 1, as the case of n is even or n is odd. So we can leave that for now. And as well, we have sine n of 0 here, which will cancel out to give 0. And we also have cos n of 0, which is 1 in both cases. In both cases of n is even and n is odd. So since everything here is turned to 0, our focus now is here. So an is equals to 1 over pi. We are left with cos n pi over n squared minus cos n of 0 over n squared. So we can evaluate a1, we can evaluate a2, we can evaluate a3. This is because of the varying in cos n pi. So when we evaluate a1, that is n is equals to 1, we have 1 over pi, and so cos 1 pi over n squared minus cos 1 of 0 over n squared, and this will give us 1 over pi, and cos pi is minus 1 over n squared, and cos 1 of 0, cos 1 of 0, that's cos 0. Cos 0 is 1 over n squared. And we have disposed something. I'm trying to look for it. Okay, see now mistake. This should be minus. It should be minus. So moving on, we have 1 over pi and minus 1 over n squared minus 1 over n squared will be minus 2 over n squared. Sorry, we should have substituted n to be 1 also. N to be 1, n to be 1, and n to be 1. And 1 squared is 1. 1 squared is also 1. And this will give us 1. So we'll have it to be minus 2 over pi. Now we evaluate for a2. So wherever we see n, we put 2. So we have cos 2 pi divided by 2 squared minus cos 2 of 0 divided by 2 squared. That will be 1 over pi from cos 2 pi is 1 and 2 squared is 4 minus cos 2 of 0, that's cos 0 is 1 and 2 squared is 4, and this will give us 0. Now we evaluate for a3. Wherever we see n, we put 3, so that's 1 over pi from cos 3 pi over 3 squared minus cos 3 of 0 over 3 squared, and that will give us 1 over pi from cos 3 pi is minus 1 and 3 squared is 9. Cos 3 of 0, that's cos 0 is 1 and this is 9. So give us 1 over pi divided by minus 2 over 9, which will give us minus 2 over 9 pi. Now if you continue further to evaluate a4, a5 as well as a6, we will see that a4 is equals to 0, a5 will be minus 2 over 25 pi, and a6 will be 0. So we can put them in order that a1 is equal to minus 2 over pi, a2 is equals to 0, a3 is equal to minus 2 over 9 pi, a4 is equal to 0, a5 is equals to minus 2 over 25 pi, and a6 is equals to 0. So we have been able to evaluate on an. Now the next thing to do is to evaluate bn. And bn from our formula is 1 over pi integral of pi of minus pi to pi f of x sine nx dx. Now in this case, we know that our f of x is in two formats of minus pi to x, and we have this to be minus pi ranging to 0, and we have this ranging to pi. So bn can then be further splitted into 1 over pi to minus pi to 0 of f of x sine nx dx plus 1 over pi integral of 0 to pi of f of x sine nx dx. So in this case, we would have to put the corresponding f of x into the corresponding range. So for minus pi ranging to 0, we have the f of x to be equals to minus pi, just like we have done in calculating an. And for 0 to pi, the f of x is x sine nx dx. So bn, when pi cancels minus pi, we have minus 1 integral of minus pi to 0 of sine nx dx plus 1 over pi integral of 0 to pi of x sine nx dx. So now we apply also uv, where we say integrating uv will be equal to u v1 minus u prime v2 plus u prime prime v3, and it continues. And we know that our u is x and our v is sine nx. So u prime, which is differentiating u, will give us 1, and u prime prime, which is differentiating 1, will give us 0. And our v1, which is integrating v, and which means integrating sine nx dx, will give us minus cos nx over n. And our v2, which means integrating v1 with dx, we are integrating cos nx over n because v1 is cos nx over n, and this will give us minus sine nx over n squared. So we solve bn, and solving this, that means we are integrating sine nx, we will have minus 1 into cos nx minus cos nx over n, ranging from minus pi to 0. Also plus 1 over pi, we start with u is x, v1 is minus cos nx over n, minus u prime, which is 1, and v2, which is minus sine nx over n squared. And the range that we are using, or the limit, is 0 to pi. 0 to pi. So after that is done, we can now begin to simplify further. So minus 1 multiplying minus 1, our resulting will be cos nx over n minus pi to 0 plus 1 over pi to minus cos nx over n plus sine nx over n squared from 0 to pi. Thereafter, we add upper limit and we subtract it from the lower limit. So the upper limit for this is 0 and the lower limit is minus pi. So we have cos n of 0 over n minus cos n of minus pi over n plus 1 over pi. The upper limit in this case is pi and the lower limit is 0. Therefore, we have minus pi cos n pi over n plus sine n pi over n squared plus sine, sorry, minus, now dealing with the lower limit, 0 cos nx over n plus sine n of 0 over n squared. Now, with this done, we can also recall that cos n of 0 is equals to 1, cos n of minus pi is equals to cos n of pi as even function, which can be equal to plus 1 or minus 1 as the case may be. Sine n of pi is equal to 0 and sine n of 0 is equals to 0. So therefore, we can reduce it further and say this will become 0 because we are multiplying by 0 here. This will become 0 because sine n of 0 is 0. This also becomes 0 because sine n pi is equals to 0. So we are left with these three cosine function. Say Bn is equals to cos n of 0 by n minus cos n of minus pi over n plus 1 over pi into minus pi cos n of pi over n. So simplifying further, we have Bn is equals to cos n of 0 is 1 over n minus cos n of minus pi is cos n pi according to even function, and this will have minus pi cos n pi over n. Now with b of n equals to this, we can evaluate b1, we can evaluate b2, we can evaluate b3, and we can also evaluate b4. So when you substitute 1, we realize that b1 is equals to 3 over 1, which is 3. b2 is minus 1 over 2. b3 is 3 over 3, which is 1. And b4 is minus 1 over 4. So we have evaluated b1, and let's go back and remember what we evaluated a naught as well as an. So our a naught is minus pi over 2, and our a1, a2, a3 as an are this. Let's copy and let's paste. So we can write our an up to a4. So a1 is equals to minus 2 over pi, a2 is equals to 0, a3 is minus 2 over 9 pi, and a4 is equals to 0. You can just do up to a4. Now let's delete this. and we call also that our a naught is minus pi over 2. Now we'll be applying our formula of Fourier series, which says that f of x is equals to a naught over 2 plus summation of n is equals to 1 to infinity of an cos nx plus bn sin nx. So with that done, we can now substitute our a naught, our an, and our bn. And we know that an can span from a1, a2, a3, and a4. bn can also span from b1, b2, b3, and b4. So we can further simplify our f of x to be a naught over 2 plus a1 cos x plus a2 cos 2x plus a3 cos 3x plus a4 cos 4x, and also plus b1 sin x plus b2 sin 2x plus b3 sin 3x plus b4 sin 4x. So then we begin to substitute. Our a naught is minus pi over 2. So f of x is equals to minus pi over 2 multiplied by 1 over 2 plus a1, which is minus 2 over pi, minus 2 over pi cos x plus a2, which is 0 plus 2x plus a3, which is minus 2 over 9 pi plus 3x. a4 is 0, 0 cos 4x plus b1, which is 3, 3 sin x plus b2, which is minus 1 over 2, minus 1 over 2 sin 2x plus b3, b3 is 1 sin 3x, and plus b4, which is minus 1 over 4 sin 4x. Now simplifying further, we have that our f of x is equal to minus pi over 4 plus minus, or is it plus minus 2 over pi cos x. This cancel out to give 0, and as well as this minus 2 over 9 pi cos 3x plus 3 sin x minus 1 over 2 sin 2x plus sin 3x, and this will give us minus 1 over 4 sin 4x. Now, a question might come further and say that we should, from here, we should prove that, we should deduce that 1 pi squared over 8 is equal to 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared, and it continues. So the way to do that is to substitute x to be equals to 2x, or 2 pi, sorry, in f of x. So wherever we see x, we substitute 2 pi. So we have minus pi over 4 plus minus 2 over pi plus 2 pi plus or minus 2 over 9 pi plus 3 2 pi plus dot 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 plus 3 sine x, that means sine 2 pi minus 1 over 2 sine 2 pi plus sine 3 2 pi minus 1 over 4 sine 4 2 pi. Now we can see these 4 are multiples of sine 2 pi, and we know that sine 2 pi is 0, so this will give 0 0 0 and 0. So in essence, we have in minus pi over 4 and cos 2 pi is 1. So this will give us minus 2 over pi, and multiples of cos 2 pi is also 1, minus 2 over 9 pi plus dot dot dot. So let's bring minus pi over 4 to the other side. So we have it to be pi over 4, and we can factorize with minus 2. Okay, so we have minus 2 over pi, and we have 1 minus 1 over 9, sorry, plus 1 over 9, and it continues. So when we multiply both sides, we have it to be pi squared over 8 is equals to 1 plus 1 over 9 plus dot dot dot. So we can interpret it as pi squared over 8 is equals to 1 plus 1 over 9 is 3 squared, and 1 here is 1 over 1 squared, and then we can continue the series. And this brings us to the end of this video. In our next session, we'll be talking about even and odd functions.